Hello, welcome to our presentation on air pollution in the USA. This work was carried out as part of a course project Data 230 Data Visualization by Group 6. Today we'll explore the extensive impacts of air pollution, focusing on different pollutants, their sources, and their effects on the environment and public health. So, as we know, air pollution is one of the most daunting challenges facing in urban environments globally. So, it arises from various sources such as vehicle emissions, industrial discharges, and even natural phenomena like wildfires and dust storms. So the pollutants include particulate matter like PM 2.5 and PM 10, nitrogen oxide, sulfur dioxide, carbon monoxide, and ozone, each with distinct sources and health implications. So let's go into our PPT. Here, pollution involves the introduction of harmful materials into the environment, significantly affecting the quality of our air, water, and land. So in this project, we delve into air pollution, which is a critical environment threat due to various human activities and natural processes. Problem statement is that despite being frequently overlooked, air pollution has a profound negative impact on health and quality of life. So our goal is to utilize sophisticated data visualization tools to uncover and present clearer insights about air pollution in the United States. The motivation and objective of this project is to provide meaningful insights into the extent, sources, and impacts of air pollution using visualization techniques. We aim to identify high-risk areas and advocate for effective policies and interventions. So this is the workflow diagram for a project where we have collected the data and pre-processed it, and we had this exploratory data analysis, we visualized and data analysis, and we created dashboards, and we concluded and reported it in a document. So for this, we have two types of data sets, and this data set one consists of different factors like pollution, pollutants, meteorological features of different states in America. And this data set two consists of different factors like AQI value, AQI category, city name. So this has no missing values in the data set. So this is a flow diagram of all the factors, whichever we took from the data set. So for exploratory data analysis, first we began with cleaning the data set, and then we did some descriptive statistics and trend analysis, spatial visualization, factor analysis, comparative analysis, insight discovery, and we visualized using few techniques. So let me show you the visualization we done with Python first in live. Now I'm opening my Jupyter. So here I have the code of all the visualizations we have done. So let me run it live. Yeah, now I ran the entire cells. So here we loaded the data set and then we formatted it to create some visualization. The first visualization is chloropath map. So here in the code, we have given all the attributes whichever we want to show on the graph. So we can zoom in and zoom out this one. This chloropleth map gives the average PM 2.5 levels by state. So it visualizes average PM 2.5 pollution levels by state across United States using a color gradient that ranges from yellow to red. So the deeper red here, hues on the map indicate states with higher average PM 2.5 levels, suggesting significant air pollution, while states depicted in yellow, which is lower here, says lower PM 2.5 levels, indicating relatively cleaner air. So this regional differentiation is likely influenced by factors such as industrial activities, population density, geographic features that can trap air pollutants. So this data highlights trends where certain central and eastern states show elevated pollution levels compared to other regions. So if we select a state, we can see the PM2.5 levels, maximum levels. So this yellow color says lower PM2.5 level, which is negative here. This deeper red says higher PM2.5 level. And next we have a bar chart. Here we have used Plotly to create this bar chart. So this bar chart depicts the average O3 levels by month, illustrating a seasonal trend in ozone concentration. So here the level start lower in January and gradually increase, peaking in June before starting to decrease again towards December, which is end of the year. So this pattern reflects the a typical seasonal variation in ozone production, which trends to increase in warmer months due to higher sunlight exposure and temperature catalyzing the reactions that produce ozone. So the use of color gradient from purple to green emphasizes the rise and fall of ozone levels with the highest concentrations shown in bright yellow in June, indicating the peak of ozone layers. So here the Jan has ozone average level of 18 and June has 26, and gradually it started to decrease after June slowly to December with a 21, which is indicated with green. So next we have a scatter plot. This scatter plot displays the relationship between PM2.5 versus O3 median levels by state. So here we have 4 states, which is Texas, California in green, New York in red, and Florida in purple. So the plot for Texas shows a relatively consistent O3 level regardless of PM2.5 levels, but consistently low O3 levels. New York is categorized by a cluster of high O3 levels. New York is having high, and then Florida's data points indicate both low for O3 and as well as PM2.5. And this California displays wide range of PM2.5 level, but consistently low O3 levels. So this visualization is instrumental in highlighting how the concentration interaction between PM2.5 and O3 levels can vary significantly from state to state. So these effects reflect the differences in local industrial activities, traffic volumes, and environment policies too. So next we have a line graph. This illustrates the median PM2.4 level across 5 major cities, which is mentioned here, which is Atlanta, Fresno, Houston, Los Angeles, and San Diego. So it is an interactive time series of PM2.4 levels for these 5 top cities. So if we observe, this graph is taken from January 2019 to October 2020. So dates are mentioned in the x-axis. So if we observe this graph, the Los Angeles experienced, which is marked as purple line, experienced a significant spike in PM2.5 level around July 2020. Yeah, standing out against the generally consistent levels observed in other cities. So this graph showcases the variability in air pollution across different urban areas, with each city exhibiting unique trends and fluctuations over the observed period. So next we have a sunburst chart of maximum NO2 levels in top 20 states. So we have taken 20 states. So if you can see Texas, California, New York as prominent because we took it as example here. So each state is represented with segments indicating NO2 levels for different years, showcasing trends and comparisons across states over time. So the charts color coded design effectively differentiates between states and years, providing an visualization of NO2 pollution dynamics. So if you click on each bar, you can see the information written, which is the state, city name with NO2 value with the state. So yeah, next we have a Sankey diagram, which is a visual representation of pollution and population categories across various states. So all states here uniformly flow into a single pollution category labeled moderate, which then diverges into four population mobility categories, which is low, very high, medium, and high. So this indicates that while pollution levels are consistently categorized as moderate across the board, the impact on population mobility varies, potentially reflecting different urban planning and public health responses to environmental conditions in these states. So this diagram simplifies complex data, offering a streamlined view of state level population pollution impacts on population behavior. So these are the Python charts which we did. Next, I'm going to show you Tableau visualizations. So now I'm excited to demonstrate our Tableau dashboards, which delve into weather conditions and their impact on pollution levels. So these dashboards and sheets are designed to provide an in-depth analysis of various metrics, including wind gusts, wind speed, dew counts, humidity, temperature, and etc. So this is sheet 1. So this is a tree map that provides a visual representation of the average AQI value across different state. So each block within the tree map represents a state with a size of each block proportional to the AQI value it represents. So let's talk about the color we did. So the color gradient from red to green indicates the severity of the air quality. So darker red denotes higher AQI score, suggesting poorer air quality, while green indicates lower AQI scores, representing better air quality. So how do we identify here? So each block is labeled with the state's abbreviation alongside the average AQI score for that state. For instance, if you take Houston, there's an average AQI value of 103, which is highlighted in red, indicating significant concerns regarding air quality. So the states are arranged from left to right and top to bottom based on their AQI score, starting with the highest. This layout helps viewers quickly identify the states with the most critical air quality issues, as well as those with relatively better conditions. So next we have another tree map where it includes highest average AQI, another map where it includes the various air pollutants, including carbon monoxide, nitrogen dioxide, and other elements. So here we have given the marks which calculates the average, which shows the state. So same, it's indicated from red to green. The color gradient is from red to green. Next, we have a cluster plot, which shows the trend over 2019 and 20 years. So the x-axis represent the miles, sorry, x-axis represent the months, and the y-axis we have all the elements which affects the pollution. So a higher so each color, each factor, each element is described with a particular color, which we used for carbon monoxide is pink, for NO2 it's orange, brown, green, gray, and yellow. So these patterns and seasonal fluctuations in pollutant levels, where the increase of O3 during warmer months, or variations in PM 2.5, or variations in PM10. So we can say that all these variations might happen because of many reasons, such that COVID-19 pandemic, which had significant impacts on emissions due to reduced human activity too. So next we have, this is we have created so many graphs with this date in for this data set. In the left corner, you can see the tables and all the elements which we used in which we collected from the data set after cleaning it. So these are the graphs we generated. This is a wind speed with temperature, wind gust, dew count, humidity with temperature, humidity with pressure variance, ozone, a PM 2.5, again PM 2.5 for all the cities, NO2, NO2 with some PM10, PM10, SO2 variants with all the cities. So we have created dashboards for this. So let me explain the dashboards now. So here we have weather conditions and pollutions. So this wind gust, which is a graph which depicts maximum wind gust speed recorded each quarter. So the x-axis represent the quarter of date from 2019 Q2 to 2020 Q4, and the y-axis shows the maximum wind gust speed in kilometers per hour. So each bar is color coded based on the intensity, with darker shades indicating higher speeds, which depicts the total count of wind gust measurements recording during each quarter. So if you can see that we can see what's happening in each quarter for each variance. So next we have wind speed. In this histogram, it displays a distribution of maximum wind speeds observed categorized into bins. So the x-axis categorizes the wind speed into bins, and the y-axis represents the frequency of observations falling into each bin. So this graph helps in understanding the most common wind speeds, which is crucial for accessing the potential for wind to disperse or accumulate pollutants in an area. So next we have dew count. So this graph shows the number of observations where dew was noted, categorized by the minimum and maximum temperatures at which dew occurred. So the bars are segmented by the year of observations 2019, 20, and 21, with different colors indicating, with the orange color indicating different years. So this visualization is significant because it combines temperature data with dew occurrence, linking to conditions that could affect humidity and thus pollutant concentration. So the peak has, so in 2019 July, the peak dew max is 26,747, where the temperature minimum is 24,000. And in July 2020, the dew max is 24,000, where the temperature minimum is 22,000. So next we have wind speed with temperature. So this line graph illustrates the relationship between maximum wind speed and the temperature. The x-axis represents wind speed max bins, while the y-axis has dual scales showing both wind speed and temperature count. So this graph highlights how wind speed increase with temperature, a vital factor in understanding how warmer conditions might enhance the dispersion of air pollutants. Here you can see that the blue line, which is max wind speed, is increasing with respect to the max wind speed and the temperature count. Next, we have humidity with pressure variance. In this graph, we have a relationship between maximum humidity levels and variance in atmospheric pressure by humidity levels. So the x-axis sorts data by humidity bins and y-axis measures average pressure variance. So this graph is useful for studying how different levels of humidity correlate with changes in atmospheric pressure, which can influence weather patterns and air quality. So you can see when you click each bar, you can see what the maximum humidity bin is and the average pressure varies for each. Next, we have humidity with temperature. So the previous graph was with pressure variance. Now this is with pressure with temperature. So the median humidity levels alongside median temperature max values also sorted into bins based on humidity levels. So this graph is key for analyzing how humidity and temperature interact, which is crucial for understanding conditions that could lead to increased pollution levels or potential weather events. So we have created 3 dashboards. So next dashboard is for pollutant distribution across country. So this left side tree map displays the distribution of PM 2.5 levels across various countries. So if we click on each bar, it says which country and what the PM 2.5 median is. So color coding is from light to dark signifies increasing concentration of PM 2.5, providing a visual representation of areas with higher pollution levels. So in the right side of the same graph, the larger and darker block, the higher the PM 2.5 concentration, which allows viewers to easily identify with significant pollution. So we have the other chart, which is for PM10 with max, min, and variance, where in the x-axis we gave the months and in the y-axis we gave the elements. So we have taken 3 colors, pink, blue, and orange. So if we see for the March, it is around the PM10 max is around 1,29,000, and for PM10 it is same. And for March in PM10 variance, it is 1.44 and also if we see there's a gradual increase and later it started to decrease depending on the month. So next we have ozone levels by month. So this tree map displays ozone concentration levels by month. Each block represents a month with the size indicating the relative concentration of ozone recorded in that particular month. So the varying shades of blue represent different intensity levels, helping to visually capture the seasonal dynamics of ozone concentration. So in the month of May, the count of O3 is 3,199, but in the month of January, it is 3,212. So it depends on the month. So next we have SO2 variance. So this tree map illustrates the variance in sulfur dioxide levels across different countries, represented by a block with varying sizes indicating degree of variance in SO2 levels. So the color variation from light to dark green portraits to low to high variability respectively. So if you click on a single country, you can see the median. So next for NO2 also, if we click on a particular country, we get to see what city is it and what level the NO2 variance is at. So this is on another dashboard which shows the pollutant distribution across country. Excuse me. So next we have pollution distribution across city. First we have ozone, which is a line graph. This presents mostly variance in ozone levels throughout a specific time period indexed by month. So the x-axis labeled as month of date sequentially numbers the months, while the y-axis measures the variance in ozone variance in ozone levels in millions. So the graph shows a peak in ozone variance, indicating that during certain month, typically the warmer months, there is substantial increase in ozone fluctuation. So this could correlate with increased sunlight and higher temperatures, which accelerate the chemical reactions that produce ozone. So the sharp decline following the peak suggests to return a lower variance levels likely to due to seasonal changes affecting ozone production. Next, we have NO2, which is a tree map. This tree map displayed here visualizes the distribution of nitrogen dioxide NO2 levels across different cities. So each block represents a city with the size indicating the relative amount of NO2 detected and the color depth signaling the intensity of NO2 pollution. So the cities like Manhattan, Brooklyn, Seattle show larger dark colored blocks highlighting their higher NO2 levels, which could be attributed to denser traffic and industrial activities. So this visualization allows viewers to easily compare NO2 pollution across different areas and identify pollution hotspots. So next we have SO2 variance. So this tree map illustrates the variance in sulfur dioxide SO2 levels among several cities. So similar to the NO2 tree map, each city is represented by a color-coded block where the size and color saturation reflect the SO2 variance. So cities like Jacksonville, Detroit, San Francisco are shown in larger, darker, not San Francisco, but the other shows in darker blocks might experience more level of SO2 while compared to the lighter blocks. So next we have PM 2.5, which is a tree map. Here, this visualization shows particulate matter PM 2.5 levels across major cities, which each city's PM 2.5 concentration depicted by uniquely colored blocks. The size of each block correlates with the concentration level, providing a clear visual representation of cities with more severe PM 2.5 pollution, such as Los Angeles and San Diego, might pose a significant health risk, particularly in terms of respiratory and cardiovascular issues too. Next, we have PM10. Here, this chart tracks the trend of PM10 levels throughout the year, with the x-axis representing months from January to December and the y-axis depicting PM10 levels. So each point on the graph is annotated with the exact PM10 measurement for clarity. So the chart shows peaks and valleys indicating seasonal variations in PM10 levels, possibly influenced by like changes in weather conditions such as maybe the wind patterns, humidity, which can affect the suspension and dispersal of particulate matter. So these are the three dashboards we created to show how interactively we can create and make the audience know easily with the colors and the patterns to identify the pollution levels. So this is the documentation we prepared, project for PPT we prepared for the project. So in conclusion, I can say that the analysis of US air pollution data reveals the complex dynamics of air quality and its significant impact on like public health, environment, and overall quality of life. So through in-depth search, visualization, and data analysis, we have gained valuable information about the spatial and temporal patterns of air pollution, which influences factors and possible mitigation strategies. So some regions exhibit consistently high levels of air pollution, posing significant health risks to residents. By promoting the adoption of clean energy, strengthening air quality regulations, investing in mass transit and active transportation infrastructure, implementing green building standards, and engaging communities, we can reduce air pollution and improve air quality. So in the future, there are numerous directions that air pollution mitigate in the US could go. The following are some possible directions for further research and action might be like conduct longitudinal studies to track changes in air quality over time. A long-term data collection and analysis can provide a light on how changing environmental factors, alterations in the population, and advances in technology affect the amount of air pollution. Or we can use predictive models that use historical air quality data to forecast future pollution levels under various scenarios, such as changes in industrial activity, traffic patterns, and other conditions. Yeah, thank you.